All right. So as promised, here are a couple of examples of momentum conservation in 2 dimensions. These problems are fairly difficult because you just have to keep up with your accounting in multiple directions. The idea of explosions in 2 dimensions also gets a little hairy, so I'll spend pretty much this whole lecture just talking about these two examples. Hopefully it doesn't take too long to get through them. But I've got the math set up to where I can essentially talk about the math and give commentary, and it won't be just me doing algebra the whole time. So hopefully this will be helpful where you can see the math all laid out, but then you can get my thoughts as we step through it. So in cases where momentum is conserved, remember this would be an isolated system. This is an isolated system. Oh, my handwriting is terrible. I promise when I'm not writing on this thing, I have wonderful handwriting, but this just looks like crap. So in an isolated system, we know that what we start with is what we end with. Um, and this is also the case in each individual direction. So in the x direction, what we start with is also what we end with. So we have our initial, so we can say our x initial pieces, pix1, pix all the way through n. We could have a million objects if we wanted them. It's whatever. So the total momentum in the x direction, so sum pix initial has to equal the total momentum uh, when we're done. So the total momentum, the total final momentum in the x direction. Same with the y direction. What we start with. So here's the sum. Initial y. So we could have 1,000 particles or just 2, and they'll all have an x and a y momentum. We add up what we start with in each direction. It's got to equal what we end with. And that's the whole idea. We're going to do essentially, you could think about it almost like free body diagrams and force problems where you have forces in the x direction and the y direction, but you're going to do your accounting separately. It's the same idea. So let's look at a quick elastic collision here. You remember an elastic collision. Uh, this is one where we have two objects that hit, and they stay together, and then they have a common velocity and common direction afterwards. Also for this problem, I pulled this from the textbook, and it does reference a previous problem that we're not going to use. So if it feels like you're watching the sequel to a movie you missed, don't worry about it. So we have this 2,000 kilogram Cadillac and a 1,000 kilogram Volkswagen. Okay, from a previous problem that apparently they crashed into each other. So just after leaving the auto body shop where they've been repaired, they actually meet each other again. Okay, so the stoplight has just turned green. And the Cadillac heads north. Okay, and drives into the intersection. Okay, we see that here. The Volkswagen traveling east fails to stop. The Volkswagen crashes into the left front fender of the Cadillac. Then the cars stick together and slide to a halt. Officer Tom, responding to the accident, sees that the skid marks go 35 degrees northeast from the point of impact. And then the Cadillac driver, who keeps a close eye on the speedometer, he reports that he was traveling at 3 meters per second when the accident occurred. So we know how fast the Cadillac driver was going when the accident occurred. But now the question is, how fast was the Volkswagen going before the impact? So we're after this speed here. So this is an inelastic collision. Oops, I just realized this should say inelastic. There we go. Okay, so this is an inelastic collision. The total momentum of the Volkswagen plus the Cadillac, uh, this whole system here is conserved. Now, notice we have our two cars crashing into each other. They're sliding off at an angle, and this angle, of course, has an x component and it has a y component. So now we're dealing with momentum in two dimensions. So our total momentum, uh, we could have some of it be in the x direction and some of it be in the y direction. So in the x direction, let's think about it first. We have the initial x momentum of the Cadillac here, plus the initial x momentum of the Volkswagen. Now, if you think about it, the initial x momentum of the Cadillac should be 0. I mean, if we look at our initial diagram up here, there's no side-to-side motion, so the momentum here in the x direction for the Cadillac should be 0. Now, whoops, we know that this is going to be 0, so at least in the x direction, all of our final momentum, so all of this over here, all of our final momentum, well, all of that is actually just coming from just the Volkswagen. So the Volkswagen is supplying all of that x momentum, or the momentum in the x direction after the collision, because the Cadillac's just not moving side to side. Okay, now let's think about the y direction. I'll even change colors for this. Okay, now we have the initial y momentum of the Cadillac. We know that it does have a y momentum, it's moving up, and we've defined the up direction, the forward direction, as y for the Cadillac, positive y. And we also have the Volkswagen, but if you notice, unlike the Cadillac, the Volkswagen is not moving in the y direction at all. It's not moving left or right from its perspective. So that's 0 as far as the y momentum. Okay, so that means in the y direction, so the forward direction with regards to the Cadillac, even though they smash together and have a common mass and a common velocity afterwards, all of that final momentum in the y direction, all of that is just supplied by the Cadillac. Okay, so at least for this problem, and this is not always the case, you can think about it in terms of in the x direction, the final, let's change back to red. In the x direction, the final momentum is supplied by the Volkswagen, but in the y direction, the final momentum is supplied by the Cadillac. All right, so we have these two equations. Let's set them up and see what we can come up with here. All right, so from the x direction, we know we have, let's see. Yeah, okay, so from the x direction, we know we have the Cadillac here. We know we have the Volkswagen. What we want to know, remember, we're trying to figure out how fast this Volkswagen was going. Was this guy speeding? Was he not speeding when he ran this light? So I've got it in red here, what we're after. We want to know what the Volkswagen speed is. So again, we've set up our equation. We know that some of this might be 0. So let's go ahead and solve for the variable that we want. So we'll go ahead and solve for the velocity of the Volkswagen, the initial velocity in the x direction. Remember, it doesn't have a y velocity. It wasn't moving left or right. Okay, so this is a simple subtract this term over, then divide both sides by mv. Okay, and then we're left with this second equation here. Now let's think about what we have. We know the mass of the Cadillac. We know the mass of the Volkswagen. We know the mass of the Cadillac. We know the initial velocity in the x direction of the Cadillac, which is the 0 part. And we know the mass of the Volkswagen. We have one problem here. We don't know what the final velocity in the x direction is. Actually, we can actually just call this a common velocity, right? Because it's got to be the same for both. If we want to simplify it, we can just call it VF. Um, so let's get this final velocity. I'm going to erase that since it is in the x direction. I'll leave it. We do know our mass of the Volkswagen. Okay, so let's see. We have two equations, though. We have the x direction. We also have the y direction information. So maybe we can actually get this unknown piece here. Maybe we can actually get that from the y direction. So let's jump down and think about our y direction information. Same thing as the x direction. We've got our two pieces, the momentum of the Caddy, the momentum of the Volkswagen. This has to equal their combined masses because they're smashed together. And that's at least we're in the y direction. So here we have the final velocity in the y direction. Now, so what I can do, you got to remember that this velocity here is in the y direction. This is not the same. So this does not equal the velocity in the x direction per se. However, what I was talking about earlier, where we could just sort of ignore the x component for a moment, let's think about it this way. What we can do is we can rewrite this y component because we know that the y component of the velocity, because you'll remember from the picture where the two cars are moving this way, and then we had this angle in here, it's like 35 degrees or something. So what we can do with our final velocity, final momentum, for the y component, we can write it as that total final velocity, except we'll just grab the y component. So that'll be a sine function, sine of the angle. Okay, so all I'm going to do is I'm going to replace Vy final with the total velocity with the magnitude of that velocity vector sine theta, and that's the same thing as my velocity in the y direction. All right. Now, since I've replaced this, what I'm going to do is I'm going to solve for the overall length of the vector, not necessarily the value in the y direction, but the value. I'm going to draw it up here. So I'm not solving for this piece here in red. I'm solving for the total length here that I'm drawing in blue. And I did that just from substituting in the sine theta here in my third equation. So I'm just going to solve for this VF, and it's just algebra. Divide the total mass over, divide the sine over, and then I'm just left with VF on that one side. So in this situation, I actually know all the parameters. I know masses, I'm good to go. I know their velocities. I know the total mass at the end, and then I know the angle. So I can plug all that in, and it turns out the overall speed or the overall velocity of this amalgamation of cars is actually 3.5 meters per second at 35 degrees. All right, now I have my overall vector. I can take that and then put it back up here in my original equation. Okay, so now we have this value in the x direction. Well, we have this value from the y direction. This is the overall velocity. Let's plug this into the x direction. So what I'm going to do is I'm going to change. You'll notice I've done it here. I'm going to change the Vx final. Well, I know in the x direction I need a cosine. So I'm just going to rewrite it. The total overall length of the vector times cosine of theta will be my x direction. And now it turns out, let's see, yeah, I know everything. I know the mass of both cars. One of them, fortunately, the velocity in the x direction 0, so that's gonna go away. That's the Caddy, so that whole term is just 0. I know the mass of the Volkswagen. I know the angle. So from here, it's just literally replace your variables with numbers and plug and chug. So it turns out that the velocity of the Volkswagen, so velocity of the Volkswagen It was actually quite high. It was 8.6 meters per second in the positive x direction. So we did get a positive value because it was in the positive x direction. So all that checks out, and looks like this guy was going pretty fast to have run a red light. All right. So now let's talk about this next problem. This one's pretty wild. There's a lot of math. So this is going to be probably one of the harder problems that you'll come across in this topic. So the previous problem, we had this inelastic collision. Two objects came together into one and kept moving with a common velocity. Here, we're going to talk about an explosion where we essentially do the same thing, but backwards. We have one object that gets blown into multiple pieces. So we have a 10-gram projectile that is traveling east at 2 meters per second when it suddenly explodes into 3 pieces. Okay, so we have 3 components to deal with. A 3-gram fragment is shot due west at 10 meters per second, while another 3-gram fragment travels 40 degrees north of east at 12 meters per second. So what is the speed and direction of the third fragment? So you'll notice for this third fragment, we've got 2 unknowns. Okay, so we've got our drawings here before and after. We've got everything labeled. So what we don't know, so we don't know what is the angle of this third piece. We also don't know what the final velocity of this third piece is. So we have 2 unknowns we're trying to solve for, which means we're going to need 2 equations. Luckily, this is a problem in 2 dimensions, so we're going to have an x equation and a y equation. So it'll be like pre-calc again, for those of you that have pre-calc, or gosh, let's see, in high school it'd be math 2, math 3, I guess, for those of you that did Common Core math. All right, so let's think about the x direction. So we know we have a total mass and a total velocity that we're starting with, okay, because we have our initial, our before. Okay, everything's happy and joyful and all in one piece, so we're going to call it big M, big V, because it's one big clump of stuff before it explodes. So this is our initial momentum, is what we start with. But then the after is when we have 3 separate pieces. So we have the final momentum, and this is just the x direction, the final momentum of objects 1, 2, and 3. Now we have these Vx's floating around, so I'm going to go ahead and change this to, instead of just the x components, I want to keep it in terms of the actual overall length of the vector. You'll notice we have these overall lengths of vectors, right? We don't have their components listed. So what I'm going to do, let me erase this. It's the same trick I used in the last problem. I'm going to take my x component and write it in terms of the overall length of the vector times cosine, because that's the same thing. If you notice here, for the second piece of this object, the x component for the second piece, and I'm going to draw it down here in the bottom left. That's actually, it's all in the x direction anyways. So because it's all in the x direction, we don't have to worry about breaking it up into pieces, or breaking up the x and y components of objects 2 or piece 2. So we're just going to leave it as v final 2. And then same thing again. I'm going to break up the velocity of my third piece of this explosion. So instead of writing it as just the x component, I'm going to write it as the length of the overall unknown vector times cosine of the unknown angle. So notice when I did that, I actually got both of my unknowns here in this one equation. I've got my unknown velocity. I also have my unknown angle. It's not super helpful because as of right now, I have one equation, but 2 unknowns. So let's move to the y direction. Same thing again. I've got my overall big chunk of stuff before it explodes. This is my prior, my initial. Okay, then I have all of my final momentum, my final momenta after this thing explodes, but now we're just thinking about the y direction. So I've got the object 1, object 2, object 3. And I'm going to do the same thing again. I want to get my overall vectors in there and not just their components. So I'm going to rewrite my y component of object 1 in terms of the overall final velocity of the object times sine of theta. That's the same thing as in the previous line, vfy1. Well, let's see. We know that the second object, object number 2, it's only moving in the x direction. It's moving to the west. So that's going to be 0. We don't even care about it. And I'm going to do the same thing again. So I'm going to take my third object, and I'm going to take its y component velocity. Notice it's v final y, third object. And instead of writing it just as that x or that y component, I'm going to sort of revert it back to the length of the overall vector times sine, which is the same thing as the y component, right? And once again, I have my unknown velocity and unknown angle in here. So now I have two equations, equation 1, equation 2, and I have my two unknowns. So I should be good to go. Now, what I'm going to do is I'm going to take my y direction, literally just because it's a more simple formula. See, I only have two pieces. Also, in the y direction, you'll notice that I said all this is equal to 0 because initially, if you look back here at my before picture, this overall object has no momentum, no velocity, no anything in the up-down direction, in the y direction. So that's where this 0 momentum comes from. There's nothing going on in the y direction, so I can just say, oh, it's 0, and then move on. Okay, so I'm going to take this equation in my y direction, and I'm going to solve for the final velocity, v final 3, my unknown velocity. Okay, so I've identified it here. Now I'm just going to do some simple algebra to get it by itself. Okay, so I'm going to divide both sides essentially by the mass of the third object and that unknown angle. And then I've essentially, in one algebra step, I've isolated my final velocity of the third piece of the object. Now what I'm going to do is I'm going to take the stuff from the y direction and I'm going to plug it in to the x direction. Remember, this is my x direction stuff. When I do that, I have one equation and one unknown now. See, now I have this one equation, and the only unknown thing I have is this this theta 3, so my unknown angle for the third object. Now this is where it gets a little tricky because we got to do some crazy trig and some crazy algebra to actually solve for theta, because that's all I want to do now. I just want to solve for the angle of my third object. Okay, so from the previous slide, we're just going to take the same equation and do some math. Okay, so this is just from previous. So you'll notice I've canceled out the third mass. I mean, it's an unknown mass. It's in the problem. Oops, yeah. In the problem, you notice that they didn't actually say what this third mass was, but turns out in the equation it cancels out anyway, so we don't even need it. That cancels. You'll remember that sine theta over cosine theta is tangent, but look what we have here. If we were to multiply this cosine in, we would have cosine theta 3 over sine theta sub 3. So what's going to happen is we're just going to flip this, and this works just fine. Sine. Okay, you know what? That's bad. I'm going to erase that and do it again. So instead of sine over cosine, we actually have cosine over sine here, which is actually just 1 over tangent. So we can use this relationship and just get a tangent in the denominator. So that has taken our theta sub 3 here and theta sub 3 here. So instead of having it floating around in two different parts of this equation, we've collapsed it into just one place in this equation. All right, this next step going from line 2 to line 3 looks like a lot happened, but actually not really, not a lot has happened. All I've done is I've essentially taken my denominator and multiplied it over to the left-hand side. Then I've taken all of this and divided both sides by all the crap in my blue parentheses. Okay, so that's how it gets into the denominator here, and that's how my tangent gets over here on the left. Okay, now the last thing, because I have a tangent of theta sub 3, all I need to do is just finally isolate theta sub 3, so I can just take the inverse tangent of both sides. And now I'm just taking the inverse tangent of this crazy big crap inside the parentheses here. And you'll notice, remember anything inside the tangent here, the inverse tangent needs to have no units. It needs to be unitless. So we have a mv sine theta on top. So that's just, remember sine is unitless. So this is kilogram meters per second. That looks great. So we have a kilogram meter per second, kilogram meter per second, kilogram meter per second. So it looks like even when I add these up, we'll have a kilogram meter per second in the denominator as well. So this is a good check when you're doing math symbolically. You need to make sure that you're going to wind up with the correct units. Because if we get these, if we get momentum units on the top and the bottom, they'll cancel out, and we'll make sure we wind up with a unitless number. All right, now we've solved for theta sub 3. We've got this big gross equation. Let's go through and make sure we actually have all the values, the actual numbers we need. So let's see, it looks like we have the mass of the first object after it's split apart, or the first piece of the object. We have that velocity. We have the angle for that first piece. Now let's look at the total. Remember, capital M, capital V. This is before the explosion. This is our initial condition. We know what that is because we're given that in the problem. Okay. And then we also have the mass and the velocity of the second piece of this object after the explosion. And then we also have all the information for the first piece. So it looks like we're good to go. We can put that in and very carefully put that in our calculator. And it turns out for this unknown piece, as these are exploding in different directions, it looks like this angle, I'll call it phi, since we already have a theta. Well, I guess I could call it theta 3. There we go. Looks like theta 3 is 45.9 degrees. Yeah, we'll call it theta 3. I'm so used to having thetas and phis and everything floating around. Let's see. So we know what the angle is. The last thing we need is just the final velocity. All right, so finally, you'll remember that this is actually from the y direction. Since we know what this angle, theta 3 is, we said it's 45.9 degrees, or at least roughly 45.9 degrees. Okay, now we started with two equations, two unknowns. Now we have two equations, one unknown, because we solved for theta 3. Let's go back to the easiest equation, which is the one from the y direction. We could do this with the x direction, but it's literally more steps. So let's just use the y direction equation. So you'll remember this is actually from a previous slide. Okay. So this is what we wanted. We wanted this unknown velocity for our third object. Let's make sure we have all the information. We know the mass, we know the velocity, we know the angle of the first object, because that's what we needed, right? If you notice here, we're actually looking at the ratio between the first piece. So I'm going to say piece 1, and then We got information from piece 1 divided by information from piece 3. Okay, so we actually know all the information for the first piece in the numerator. Now in the denominator, luckily, we now know what that angle is, that unknown angle. So we know all the information about our third piece. Now you might be asking, well, where did I get that 0.004 kilograms? Well, so the idea is the mass of the third piece is just that the total mass minus the first one, the first piece and second piece. So it's just, we know what the other two masses were of those two pieces. So let's just subtract it off from the original, like, what was it? The original 10 gram, right there, the original 10 gram uh, object. Well, we just subtract off the pieces, and that's going to give us the 0.004 kilograms up here. All right, so we can plug all this in, turn the crank, and it turns out the final velocity of this third piece is 8.1 meters per second. So we can actually put all these pieces together. You know what? I'll go back and just write it in here. This will be easier. Okay, get some math back there. All right, so in this last explosion down here, we now know, and I'll do it in orange. So we now know that theta is, I'll say negative since it's below the x-axis, going down 45.9 degrees. Okay, that's the angle, and then the velocity of this third piece of this object was 8.1 meters per second. All right, yep, and I think that's it. So that was essentially just two different examples. One inelastic collision in 2 dimensions, one explosion in 2 dimensions. Again, there's a lot of algebra that goes into these problems. I didn't want to like just go through all the algebra. I think it might be more helpful for me to just provide commentary and provide notes on the math, and then if you need it for a problem set, you can go back over it, and you can do the math yourself, but then you'll have me talking about the math along the way. So that's pretty much finished up impulse and momentum. What we'll do is we'll take these ideas and then move on to talking about energy. And when we actually put momentum and energy together, we can talk about some more types of collisions and some more conservation ideas. Right now, we have the idea of conservation of momentum, which is super useful in physics, and it's one of those big laws of the universe. Then we'll move on and expand this and talk about conservation of energy as well.